Okay, good morning. So let us start a lesson. Let me review what we did before. So more or less it is independent from the previous lesson, but I go a little bit faster. So in order to motivate you about the differential equations, I started with a simple physical system. So that let us say that I have a table surface and it is lubricated so that I can get rid of friction, at least to the first approximation. And this is the system that I have. So I have a spring of spring constant, let us say it is k newtons per meter, and it is given to me, so then I connect it to a block, and the mass of the block is also given to me, and then I want to, for example, stretch this, pull it a little bit to the right, and then release it. We know from experience living in this world, this will go back and forth, yes. And and if there is no friction, it in principle goes forever like that. Okay. So now, if this is a very simple system, I want to predict what is happening to the future of the system. So in principle, what I am doing, so let us say that I start stretching. I pull this block to the right. For example, let us say it goes up to, I stretch it, for example, 5 centimeters, let us say. And then, for example, let us consider one point here up to the same point here. So let us say that this is 5 centimeters. Okay? And then when it reaches there, I start I start the clock and then release it at the same time. And then my point is that to be able to predict the location of this block as a function of time. Okay? So that's the problem that I want to solve. Okay? So I know that uh, the law governing this motion is Newton's second law. Yes? And the Newton's second law is force as a vector equals to m, the mass, multiplied by the acceleration of my object as a vector. Uh, but you know that if you want to solve a mechanics problem, you have to set up a system, a coordinate system. But because this motion is confined to move in one direction, I only need one axis. So let us try to set up our axis. So I will take the same table surface here to be my x-axis. Yes. And then for an axis, I also need an origin. So let us take the equilibrium position here to be the origin. And then I want to know that in a future time, at any instant of time, so that's important, at any instant of time, what is this x? In principle, I want to know how x is related to time. So that is what I want to answer. So I want to know the location of this block at any instant t given to me. So if you give me time, I should be able to tell you exactly where this block is. That's the problem. Okay? Okay, so if I want to write Newton's second law for this simple system, of course you know that you can write it in any direction, but I write it in the x direction. So the force in x direction is only one force. Yes? And that is the force coming from the spring side. And then you know that is Hooke's law, so it becomes minus kx. Yes? So if I stretch it by amount of x from the equilibrium position, if I want to know how much force is being exerted on the block, I have to use the Hooke's law. Minus is coming from the fact that force is always, the sign of the force is always different from the sign of displacement. Why? Because if I pull this to the right, x is positive because it is on the right hand side of the origin, and you know that in this situation the spring force is trying to pull the block back, so it will be on the left. But now assume that this block has reached here and passed the equilibrium point towards the negative values, then you know that this spring will push it to the right. So if x is negative, force is to the right, and if x is positive, force is to the left. So this minus sign is coming from this, yes, because they are different. Okay, but again, so be careful here. If I want to write everything, x is a function of time. I am lazy to write x of t all the time, but I mean x of t when I write x. So in principle, f, force, is also a function of x because it depends to x, and also depends on time because x depends on time. So we don't write these things. I just write force is equal to minus kx. Okay, and then what we need to know is about the acceleration. In physics, so you know that what is acceleration? Acceleration is the derivative of velocity. Velocity is the derivative of location, position. Yes? So what does it mean? It means that acceleration is the first derivative of velocity. Velocity is the first derivative of position. So acceleration is the second derivative of position. Okay, and then I put them in this equation. Instead of f, I write minus kx equals to m is m, but instead of a, I put x double prime. Okay, and then I simplify this a little bit. So by moving this to the other side, this is the equation that I am trying to solve. But be careful, this is completely different from normal equations. In a normal equation, I mean, for example, 2x minus 1 equals to 0. If I ask you to solve this in Math 1C, for example, you say that x is 0.5. So what you are giving me is one single number so that when I replace x with that single number, the left-hand side matches with the right-hand side. But this is completely different. Finding x here is completely different from finding x there. Because here you are just finding a bunch of numbers, in this case one single number. But here you are not supposed to give me one single number. Yes? Because the position of the particle is not one single number. Depending at which instant of time you are looking at the particle, x is different. So it means that how many x's are in principle involved? Infinitely many, one for each choice of t. And in physics, when we start the experiment, that is t equal to 0. And so t always go to positive values in physics. So when I say t here, t in physics is greater than or equal to 0. But still, there are infinitely many instants of time. For each instant, I want to know x. So I am facing with infinitely many values for x. So in principle, I want to solve this problem that when you tell me x, when you tell me t, I tell you x. I want to find x at time t. It means this is a function. So my unknown is not one single number, is a function. So a differential equation is an equation in which your unknown is a function. You are looking for a function as a solution. Yes? That's the main thing that I want you to learn about differential equations. Okay, but now to make it a little bit simpler, physicists divide this by m. So this becomes x double prime k over m x equals to 0. And then if I use the terminology used in physics, this is defined in physics to be the angular velocity. And then, or angular frequency. So what can happen here? This k over m is what? Omega squared. These are simple things, okay? Don't get distracted by these things. So I would write this equation in this form. And might be you have seen that. This is called the harmonic oscillator equation in physics. But don't be distracted by that omega, because when you want to do this experiment in lab, when you buy a net spring from factory, the spring constant is written on it, and then you can measure the mass of this block. So k and m are numbers. You put the numbers into this formula, and then you get your omega. So omega is also a given number to you. So don't let that omega distract you. This is a number. If you want, consider 5x, whatever. It's a number times x. Okay, now I want to find a solution to this. So what do? We move this to the other side. Okay. And then I am trying to, for the time being, to do some guesswork. I am looking for a function x of t, yes, so that when I differentiate it 2 times, it becomes more or less the same function with a multiplicative constant there. Okay, so if you're a mathematician, I told you that probably you just need to be very clever to be able to guess such a thing. You have a long list of functions, then you have to go through some of them to see which one has this property. But if you are a physicist and you know that this is supposed to be a physics problem in this universe, you already know that what type of motion is there here is involved, yes? You know that it goes back and forth. It is oscillatory motion, but in principle oscillatory motion is a subset of a bigger type of motion that is periodic motion. Okay, so if the motion is periodic, so you expect that the answer to this this equation should also be periodic. So there is no point to look for exponential functions there, or I don't know, polynomial functions there. You can try, but you will probably not find it, because this problem is supposed to describe this system, and this system has periodic motion. So among the famous math functions, there are trigonometric functions that are periodic, and then probably the first one comes to mind is sine function, okay? But if you just, I told you that if you just guess sine of t, that is a little bit, it's not a very bad guess, but it is not that useful. Why? Because if I take the first derivative, let me drop t here, the first derivative becomes cosine t, the second derivative is minus sine t. And if I say what is sine t is x, so I can write minus x. So if I insist to give this as an equation, as the solution, then that solution satisfies not exactly my equation, but a similar equation. Okay? So the only difference is here is this omega. If omega is 1, yes, this is a good choice. But there is no guarantee omega is 1. Omega might be another number. So this solution is suitable for this equation, but not for my equation if omega is not 1. Then I would say, okay, can I modify this in a way that it satisfies this equation? So do you remember what we did? Omega t. So we try to put sine omega t there, and then hopefully you remember the chain rule, because now it's a good choice. When I differentiate it, it not only becomes cosine omega t, but because of the chain rule, I have to multiply by the derivative of this. So what is the derivative of omega t? T is playing the role of x in math 4, yes? So omega is a constant. It is like I ask you what is the derivative of 5x in math 4. What is the answer? The answer is 5. So here, omega is playing the role of 5. T is my variable, which is playing the role of x. Okay? So don't get confused. In math 4, y and x are the variables we use. But in physics, x is the location here, and t is the time. But t is playing the role of x. Okay, so what is happening? I take the derivative of this, it becomes cosine omega t, but because of the chain rule, I have to multiply by the derivative of omega t, which gives me omega. And if you don't mind, let me write omega there. And then I take another derivative, what happens? Omega is a multiplicative constant, so keep it and differentiate this part. The derivative of cosine is minus sine, but it is not finished because of the chain rule again. So I multiply it by the derivative of omega t, which gives me another omega. There was an omega there, so if I multiply them, it becomes omega squared. And then, of course, this is simple to see. This can be written as minus omega squared sine omega t. But am I done? Yes, because if I ask you what is sine omega t, you take it off and put x instead. So this becomes x double prime equals to minus omega squared x. So that's good. So at least I was able to find an answer. So this is an answer for this differential equation, okay? Okay, so what is a differential equation? Let me give you a feeling of differential equation. Differential equation is an equation in which a function which is unknown is involved with some of its derivatives. So you see here, this is a differential equation. Why? Because what I am looking for is an unknown function x, but that equation involves the function, the unknown function, and some of its derivatives. In this case, the second derivative. So if you have an unknown, if you have an equation in which the unknown is a function, and in that equation the function appears, some of its derivatives appear, then it means that that is called a differential equation. Okay. So at least what I'm saying is that this is a solution to this differential equation. But this is, even though it is mathematically sound and good, but it is not solution to that system. Why is that? Yes, do you remember? Yeah.
Because in this case, x of 0 is
0.
but it's supposed to be 5.
5. Yes, because I just told you that if you expect to solve and predict the future of the system, one common sense is that, okay, this should also predict the initial condition, right? Yes, so if I ask you, if I accept this as my solution, this means that x of t, x at any moment of time, is equal to sine omega t. This is supposed to predict the future location of my block. But let us see what it predicts at the initial moment 0. So instead of t, I put 0, so this becomes sine omega 0, but sine omega 0 is sine 0 is 0. So it predicts that the position of the block at the initial time, when I start the experiment, it should be 0. But this is not working, yes? Because I myself told you, I pull it 5 centimeters to the right, and then when I release it, I start my experiment. So the initial position of my block should be 5, but it is predicting to be 0. So even though mathematically this function satisfies into this equation, I cannot consider this as the solution that I can rely on to predict the future of my system. Okay, is that clear? Okay, so then of course we have to solve the problem in some way. So what is your suggestion then? Might be this periodic function is not a good solution. We have another periodic function. What is that? Cosine. So let us test cosine. Okay, so if I go there and test cosine omega t, for the same reason I don't consider cosine t, I start from cosine omega t, but let me differentiate it once. The derivative of cosine becomes minus sine omega t, but because of the chain rule I have to multiply by omega, and then x double prime, again for the same reason it becomes minus cosine omega t, but I multiply by the derivative of omega t, which gives me another omega. And then if I write it, x double prime is equal to what? Minus omega squared cosine omega t. But what is cosine omega t? Is x. So it becomes x double prime is minus omega 2x. So that's also good. So it's also satisfying my equation. Yes? So this is also mathematically sound. Yes? But do you think that's also a good choice? No, let us predict. So let us see what happens for x0. What happens? It becomes what? A cosine omega 0, which is cosine 0, which is 1. That's also wrong, yes? Because the initial condition was that the location of my particle at initially is 5 centimeters, but it is predicting that it is 1. Okay, but now can you tell me how can I fix that? It is not that hard to fix this one. This solution is good when, if instead of 5, I have 1. If I had 1 from the beginning, that solution is good, you know? Yes? Okay, so how can I fix that? So even though what I'm saying is that this is a solution, but it predicts that the initial location is 1 centimeters to the right, which is of course not true. So how can I fix the problem? Yes?
Multiply by 5.
Multiply by 5, but I have to, so why don't add 5? No, so why don't add 4? Why don't add 5 to the previous case? I want to make sure that you understand when you say multiply by 5. Let me just explain to everyone. Because one alternative is to say that whatever I had before which predicted 1, I add 4 to it. Yes? Because now what happens? Do you see that? Do you think that this is a good choice? Let us check. If I check x of 0, it becomes cosine 0 plus 4. But cosine 0 is 1. 1 plus 4 is 5. So it is correct. X of 0 is 5. So why do you say 5? You multiply by 5. You said that you multiply by 5. Let us check your answer as well. If I multiply by 5, I will get this one. And let us calculate x of 0. It becomes 5 cosine of 0, which is 5. So what you said predicts correctly the initial condition. What I wrote also predicts the initial condition properly. But why do you think you are right? I will choose this one. But why? Anyone else? So why should, do you understand what's the problem? Because both of them is now fixing the initial condition. Why I prefer this one, not that one? Yes?
Because cosine oscillates between 0 and 1, so it's going to give you fractions of 5 back and forth. If you add 4, you're going to get 4 all the time. So even if it's in place 0, then you're going to get that it's 4 centimeters away.
Yes, it is not bad. It's based on physics arguments, yes. But there is a very big problem from mathematical point of view. What you said is understandable from physical problems, yes?
It doesn't satisfy the connection that x double prime equals.
Yes. So when I add it, then this is no longer the solution of my differential equation. Yes? Let us check. If I take this derivative, it becomes what? Let us do it fast. So it becomes minus omega sine omega t. The derivative of 4 is 0. But when I double prime that, it becomes minus omega squared cosine omega t. But be careful. In the previous case, I could take cosine omega t out and put x in. Yes? If you say x is this one, I cannot take this one and put x in because x is not cosine omega t. X is cosine omega t plus 4. So if I want to write something there, instead of cosine in this new scenario, I cannot write x. I can write x minus 4. Yes? And then if you multiply this back, this means that x double prime is equal to minus omega squared x plus 4 omega squared. So this is no longer the solution to the differential equation that I expect. This is indeed the solution of this differential equation, not the previous one. Okay? So that is why, first of all, I want you to understand, even though apparently it seems that when I add 4, I am fixing the initial condition, but I am spoiling the other condition that I respected before even starting that. If I add 4 to it, the initial condition is fixed, but I am solving a different differential equation, which is not the differential equation governing the system. Yes? Is that understandable? So this is not a fix. This fixes initial condition, but spoils being a solution to my differential equation. But let us check your idea. So your idea, first of all, it fixes the initial condition, but I have to make sure that it does not spoil being a solution. Okay, let us see. If I have x of t equals to 5 cosine omega t, if I take the first derivative, it becomes minus 5 omega sine omega t. If I take another derivative, it becomes minus 5 omega squared sine omega t. Sorry, cosine omega t. Okay, now let me write it like this. I would write minus omega squared out. 5 and cosine are left, so it becomes 5 cosine omega t. But what is this one now? It's again x. So it becomes x double prime is minus omega squared x. So that is the fix. Yes? It not only respects my initial condition, yes, but also the differential equation. So what I had this system, I had this differential equation, and I know that x of 0 should be 5. Bottom line is that I found this answer. Okay? So then using this, I can predict the future of the system. Yes? Is that correct? Okay, so for example, if I say that after 3 seconds, where is it? So I calculate x of 3. It becomes 5 cosine 3 omega. But omega, I told you that you know it. You multiply it by 3, you take your calculator, calculate the cosine of that, whatever it is, you multiply by 5, it is the position that you are supposed to find. Okay? So I was able to predict the future of my system. Any questions here? Okay, but then I told you another question that it was, I just want to ask what is your opinion about. So let me just put this here for future reference. Now I changed the question slightly. So I go back to my original system. So what do I do now? I do exactly the same thing, but at this point, instead of releasing it, I kick it to the left. Let us say with initial velocity minus 2 centimeters per second, for example. Because I use centimeters here, let me be consistent there. And the reason I put minus 2 is because I am kicking it to the left. So instead of releasing it, I am giving it an initial velocity. Yes? Okay. Okay, so let me try to start solving the problem from scratch, but very quickly so that you can see what I'm saying. Might be I was not very clear what I was talking about last time. Okay, so now let me, if you don't mind, so what do I know? I know that initially my location is 5 centimeters, and I know v, speed, initially is this value. Okay? Okay, now if I want to predict the future of the system with the new condition now, I want to see where it comes in, because it should come in somewhere. You know, intuitively, you know that the new motion is not identical to the previous motion. For example, in the previous motion, when I release that, it took some time so that it goes back to the equilibrium position. But I hope that you agree with me, this time it reaches to the equilibrium position faster because I'm kicking it to the left. So these two things are not identical. But let us see when it comes in my calculation. It should appear somewhere in my calculation, yes? Because otherwise I will get the same answer back. But that's what my point is, where. Because when I start solving the problem, I would write, let me do it very quickly. So I write Newton's second law, but what is the force acting on my particle after I kick? The kick is finished, because during the kick, I have another force coming from my leg. But I'm not talking from that. I am talking from the moment that the kick is done and it is going to the left. Okay? So what is the force again acting on my system? Spring force, yes? So the force is still minus kx. And exactly the same story. A is equal to v prime, v is equal to x prime, so a becomes x double prime. And I put it back here in this equation, so minus kx becomes what? mx double prime. And that's exactly the same equation, so if you don't mind, let me just do it faster. Finally, it becomes the same thing. Yes? It becomes the same thing. And then, after all these considerations, that is the same equation up there. If you don't mind, let me move it to the right, becomes exactly identical. That is exactly the equation that you see up there. What is x of 0? X of 0 is still 5 centimeters. Okay, but for these two, I find a solution. Okay, but of course, I have an extra piece of information now, but for these two, the solution is up there. What is the solution? Is 5 cosine omega t. Do you still agree that this is the same thing? Yes, it satisfies this equation based on the discussion we did here, and it also satisfies this condition. Okay, so okay, if that is the case, it means that when of course I have an extra piece of information here, yes? The extra piece of information is this. Okay, now what I am telling you is that how this last piece of information will affect this answer. It should affect, because if it does not affect, it means this is redundant. It doesn't matter if you release it or kick it. If this is redundant, the answer is again the same. But you know intuitively the answer shouldn't be the same. So my question is that how you can see this mathematically, this is relevant. Let me everyone think. First of all, do you understand my question? So you see, these two are exactly the same two up there. So that's the answer. This answer satisfies my condition here. It satisfies my condition here. In this new situation, I have an extra piece of information here. Okay? But I am telling you that this answer, this condition should somehow affect the final answer. But apparently it doesn't. Can you see where it happens that this piece of information affects my result and how? First of all, tell me why this is not suitable for containing all the information. It is suitable for the first condition. It is suitable for the second condition. Tell me why it is not suitable for the last condition.
Because it's written in terms of v and not in terms of x.
No. Check. My question is that, do you think this solution respects the last condition as well? It is not in how do you say yes or no. It is not immediately clear. This is saying something about initial velocity, but this is saying something about the location of my object. So how can you immediately say that this is not respecting this or it is respecting that? Yes?
Because when you derive xt and then put 0 into it, then you'll get 0, you'll get 1.
Yes. So that's important. So I mean, at least I want you to understand, by having the location, you cannot immediately say that this formula is respecting something about velocity yet. Unless you find the velocity and see that no, it is not consistent with it. Do you understand what I mean? Because this is telling you something about the velocity, but this is telling you something about the position. You cannot say because it is predicting something about the position, it is not consistent with what it is saying about velocity. Do you understand what I mean? Okay, so if you want to see that this condition is respecting something about velocity, first you have to derive velocity. But velocity is what? Is the derivative of this one. So let us take the derivative. It becomes what? Minus 5 omega sine omega t. Okay? And let us now calculate v of 0. Let me write here. What is v of 0 now? Minus 5 omega sine 0. Sine 0 is 0. So it becomes 0. Do you agree or not? So if I buy this solution, then my prediction about, it's not prediction because that's the initial condition. The initial condition derived from this formula is 0. So that is why this one was really good for the first system. Why? Because in the first system, I just released the block. So it means the initial velocity was indeed 0. But in this case, this solution satisfies this, but does not satisfy the last one. But this is also a very simple physical system. No one can prevent you from kicking it, yes? You kick and you want to see what the future is. What I try to convince you is that the solution is not this. And it is being seen. So this is the way it affects the calculation. Kicking or releasing comes to the next condition about velocity. So this answer was the correct answer for the previous scenario because it not only satisfies the equation, it also respects the initial condition for location. It also respects, without even I mention it, it is respecting the initial condition for velocity because in that case I was releasing the box. Yes? But it is not respecting this new condition in this problem. So how can I solve this problem? Is the question clear?
Yeah.
So my question is now this. Give me a method that I can find a solution of this differential equation which now respects two conditions, not one. This solution only respects the first one, not the second. Okay, so think a little bit about that so that I can clean the board. Yes?
I'm just guessing, could you add 2t, 5 cosine omega t plus 2t?
Okay, do you remember adding is some problematic, yes? Because when you add, you might be able to fine-tune these conditions, but you unfortunately lose being a solution in the first place. Okay? So what is a natural step to take? It's not very hard, by the way, because you know that still this is a periodic motion. Yes? Sine didn't work. Sine was a periodic function. It didn't work, even for respecting only this. Yes? And then we switched to cosine, because cosine was also another periodic function. Now we have a new problem. We were able to solve the first problem completely, but we are in trouble with the second problem. So what is the natural step to take?
Make an equation system, I guess, where you derive them and then.
No, in principle, so you see why we started looking at sine and cosine in the first place. Do you remember? Don't forget periodicness. Yes. So the famous functions periodic for us are either sine and cosine, but these are not the only ones. In Math 4 we studied them. Yes. Of course, tangent is not suitable here because tangent has its own problems. You know what that is? Why tangent? Yes. Tangent is not defined at the point. And this is usually not good in physics, because in physics you cannot say that, okay, the block comes to this point, suddenly disappears, and of course it's not quantum mechanics, okay? So it appears in the other one. So continuity of the solution is actually extremely important here. So tangent is not something that I want to check it out. But what?
So maybe like it changes the velocity of the cube when you kick it. So that maybe add a coefficient to the omega in the function.
No, but the coefficient does not work. Because if you stick to cosine, its derivative definitely becomes sine. And sine is 0 at 0. No, look, sine function is periodic, cosine function is periodic. What else we studied in Math 4 which is periodic? No. Don't start going to the myth, you know. Yes, what was the next one? The combination of them. So this was a lesson, yes? A sine x, do you remember? Plus b cosine x. That function we studied in Math 4, yes? So do you remember a formula? It was a square root of a squared plus b squared, yes? And then we had sine of x plus, I don't know, a constant c, so that tangent of c, I don't want you to disturb you because of the formulas, but you know that this combination at the end is a sine function, and a sine function is still periodic with the same period, yes? So that is exactly the combination we need. So sine alone is periodic, cosine alone is periodic, but cosine and sine does not work for my physics problem. Why not look at combination of them? Okay, so let us check a combination of them. So I would say that x of t, let us write, I don't know, a constant, whatever it is, cosine omega t plus another constant sine omega t. Okay, and then I want to see if it is possible for me to fix these two constants so that the answer that I get not only respects this condition, but also respects that condition. But do you think I am losing this condition? Because that is important. First of all, it should satisfy these conditions. After this condition, after that, it should satisfy these two. Do you think by writing such a thing, I am losing the first condition or not?
No.
Well, it's not trivial. I don't know. Did you do the calculations in your head quickly or not? If not, let us do it. Okay? So let me ask you, what is x prime? Can you do it? What is x prime? A, the cosine becomes minus sine, omega goes out, so it becomes minus omega sine omega t. What is this? The other one, it becomes omega b cosine omega t. Agree? And then I take another derivative. Okay, you can factor over. Let me take another derivative. This becomes cosine. It gives me an extra factor of omega, which will be multiplied here. This becomes minus omega squared a. Yes? And then what happens here? It becomes minus omega squared b sine omega t. But now between these two, I can factor minus omega squared out. And then what is left? It is a cosine omega t plus b sine omega t. Yes? And now what is this guy? This is x again. So it becomes x double prime is minus omega squared x. So this is a very interesting thing. Okay, that is not always true, but for this equation it is true. That cosine omega t is a solution itself. Sine omega t is also a solution itself, and regardless of these numbers, the whole combination is still a solution. So by writing a combination, I am not losing my equation. The equation is still valid. But now A and B can be fine-tuned so that it fits to two initial conditions. In principle, it can be done. Why? Because I have two unknowns. How many initial conditions I have? Two. One for location, one for velocity. So I should be, in principle, be able to fine-tune A and B so that this also satisfies both of them. Yes? So let us check if it is possible or not. Okay, so what is my goal? My goal is to fine-tune A and B so that not only x of 0 is 5 centimeters, but also v of 0 is minus 2 centimeters per second. That is my goal. Okay, x of 0 is 5. What does it mean? It means that when you replace t with 0, the output should be 5. So it means that I go to x, replace t with 0. If I replace t with 0, cosine 0 is 1, so it gives me a. If I replace t with 0, sine of 0 is 0, so it gives me nothing. This is supposed to be 5, so I found a. Yes? But now how can I fine-tune the second condition? The second condition is not about location, it's about velocity. So I cannot use this formula because this formula is for location. But you see the formula for velocity in front of you, this is it. So this is the velocity because that's the first derivative. So this means that this is the velocity at any instant t of time. But I want to fine-tune these parameters so that it satisfies the second condition, meaning that if I replace t in v by 0, the output should be minus 2. So let us do that. I go here and replace t with 0. What happens now? Sine of 0 is 0, so that's totally gone. But cosine of 0 is 1, I get omega b. So this means that omega b should be equal to minus 2 centimeters per second. Yes? I'm looking for what? I'm looking for b. So what is b? b is minus 2 over omega. Don't be distracted by omega because I told you from the beginning omega is a fixed given number. Yes? So I found b. Okay? And then what is my solution now, finally? So if I write x double prime equal plus omega squared x equals to 0 with two more conditions, okay, the final answer is what? X of t is equal to what? A, which I found to be 5, cosine omega t, plus b, which I found that weird number, sine omega t. That's your answer. Okay, so the prediction, so you see it affects, and now you feel that at least this is good, you know, because this now, in the previous case, we didn't have this term. In the new case, we have this term extra. So at least you can feel that is good, because now the new motion is different from the motion of the previous system. Okay, so is that understandable? So what I'm trying to tell you is that these are very important things that I want to now put them under official definition. So if you have a differential equation, what do you expect to see? When I say that this is a differential equation, it means that you see an equality. In that equality, something is unknown because that's an equation. But what is that unknown? Is not a number, is a function. Okay? And then not only a function, the function with some of its derivatives. The first derivative, the second derivative, I don't know, a mixture of a lot of derivatives. If I have an equation in which the unknown is a function, and I have a relation between that unknown function and some of its derivatives, that is called a differential equation. Yes? This is a definition. Something that I want to define for you is the notion of order. Don't say degree. Degree is something else. You don't study that, but order. When I say order of a differential equation, I mean the highest derivative, the order of the highest derivative in the differential equation. So here I have x and I have x double prime. So what is the order? The highest order derivative that appears in the differential equation is called the order of the differential equation. So what is the order of this differential equation? 2. So that's order of my differential equation is 2. So I want you to know this terminology in differential equations. Yes? Okay, and now these two extra conditions that I write, they are called initial conditions. Yes? You can have one initial condition, you can have two initial conditions, and a lot other initial conditions. So these extra conditions that I impose on my differential equation is called an initial condition. And the whole package, the differential equation with initial conditions, is called an initial value problem. Okay, so I'm lazy to write it. Initial value problem. Okay, so differential equation is just this one. And initial conditions are just this one. But if you consider the full package, in which case we wanted to do the same thing, the whole package is called an initial value problem. Okay? If I just give you solve the differential equation, this is a good answer. Yes? You can say that for every choice of A and B, this function is a solution to this differential equation. But if I ask you solve an initial value problem, it means that I not only want you to give me a solution to the differential equation, but I want to give it in a way that it respects the other conditions as well. Yes? Okay. Okay, now this solution that you see here is called the general solution. To the differential equation. What is the meaning of the general solution? The general solution is a solution of the differential equation that contains as many free parameters as the order of the differential equation. What does it mean? It means that what is the order of this differential equation? 2. And how many free parameters you see in this solution? 2. So that's the general solution. So the general solution is indeed a solution that contains as free parameters as the order of the differential equation. Yes? For example, x equals to cosine omega t. Do you remember? So what was that? So for example, this one. If you don't consider the initial condition, do you remember that was also a solution? But this solution cannot be called the general solution, because how many free parameters you see there? Nothing. There is no free parameters. So a solution which is not the general solution is called a particular solution. Yes, that's a particular solution. Yes. But of course, this is not the general solution, but it can be derived from the general solution by choosing b to be 0, a to be 1. Do you remember we had another solution? The solution was, what was that? It was 5. So let me write. That was also solution. Do you remember? And for the same reason, I can multiply it by 10. You can still confirm that this is still a solution. This is a solution, but it is not the general solution because it does not contain any free parameters. But it is also derivable from the general solution. But by which choices? Choosing a to be 0 and b to be 10. I don't know. For example, sine omega t minus a square root of 2 cosine omega t. This is also a particular solution, yes, because it is a solution and it can be derived from the general solution by choosing a to be 1, b to b to be 1, a to be minus a square root of 2. Yes.
And the order be bigger than 2.
Yeah, of course. Yeah, but the problem is that can I solve it? Then no. And most of the time we cannot solve the differential equations. We have to use a numerical analysis. But the good news is that I can get close to the desired answer by any desired accuracy. I can get close to the answer that I demand according to the problem in hand. Yes. But there are some very famous one that we can solve. So this is one of them. So this appears, by the way, a lot of places in physics. And the good news is that we can solve it analytically. We can find all solutions. Yes, so actually we did it. So I use this example to motivate you about something. So first of all, you understand, let me, if I want to write, so we have differential equations. So we learned what is the meaning of a differential equation. And for a differential equation, we learned what is the meaning of order, the highest derivative that appears, the order of the highest derivative that is in differential equation is called the order. So do you remember? So we had the general solution. So let us review that. What is the general solution? The general solution is a solution that contains as many free parameters as the order. Okay? And then we have another, a particular solution. Yes? So what is the meaning of a particular solution? Is any solution of the differential equation, essentially. Yes? And then we learned about the notion of initial value problem. What do I mean by initial value problem? I mean a differential equation with some extra conditions. Extra conditions are called initial conditions. That's differential equation. The whole package is called initial value problem. Yes? So these are the terminologies that we actually learned by this introductory lecture. Is that clear? Yes or no? Okay, but now let me see what we can say. By the way, I want to test your intuition based on what we just learned in Math 4 during the last 2 lessons. Here, you see, I needed 2 extra conditions. Now my question for you is this. Do you think that I should add also another extra condition here? So you see that I didn't need any extra condition to find the solution, yes? I needed 2 initial conditions because the general solution was this. And then I have 2 free parameters that I have to adjust. So I need 2 initial conditions because each initial condition is 1 piece of information. For fine-tuning 2 parameters, I needed 2 pieces of information. So that's enough, okay? So for example, at the same time, I cannot say that I want to have this, I want to have this. This is very important. Let us ask you one question. So I write this differential equation here. Let me test your understanding, okay? I would say that this is the condition. I would put the same condition. But let me see, what can I write for you? So let me write like this. X at this moment of time, okay, pi is pi, omega is omega. I want to have x at pi over omega to be 10. And now 10 is ridiculous, so let me, because 10 it cannot happen, because it's 5 centimeters at most, but let me write it, for example, minus 2,5 centimeters. What is your opinion about solving this problem? This is also an initial value problem. This is my differential equation. How many initial conditions I have? I have 3. Okay. So what is the problem here? Can I solve this problem now? Most of it is on the board. Yes? So if I want to consider these 3, what is the answer? This answer is this one, nothing else. Yes? And now let us check this one. Okay, so if I put pi over omega instead of t, x of pi over omega is what? Pi over omega, omegas are gone. Cosine of pi is minus 1, so it's minus 5. And sine of pi is 0, so that's it. But you want to have it minus 2,5. So what is the problem? So how can I solve this problem? You can't. It means that if this is my system, I fix the initial position and I fix the initial speed, that is not under my control. What happens at this moment of time? Yes? The universe, the nature calculates everything and decides that the particle should be at minus 5. It cannot be here. Yes? And that is extremely important because of order. So order of a differential equation is extremely important concept. So order is 2. So at most, how many free parameters are there? 2. And then how many pieces of information you need? 2. So you cannot force the nature to follow what I want. As soon as you give this to the nature, nature calculates and gets something for this one, and that something is unfortunately not what you want, is this one. So don't fight, because you will not be able to fix this problem. And this comes from the nature of Newton's second law, because Newton's second law, you have acceleration, and acceleration is second derivative. So you need exactly 2 initial conditions. So that is why in physics, initial position and initial velocity are the important things that we need to know about the system. If I know the forces acting on my system, I cannot predict its future. I also need to know the current state of my system. But current state of a physical system in Newtonian mechanics is this. You need to know position, initial position, and initial velocity. So if you know the forces, if you know the initial location, and if you know the initial position, there is nothing that you can control anymore. The computer in the universe calculates and predicts where the particle is at any moment of time after that. Okay? If it was somehow the third degree equation, which is a third order differential equation, then of course I need 3 conditions. Yes? So if I have a differential equation of order 3, then I have 3. I can fix 3 initial conditions. Yes.
What would the third initial condition be? Acceleration?
No, I don't know, because in this case you can't write acceleration. You can choose 2 locations and 1 velocity. It doesn't matter. But for this you cannot do that. As soon as you fix 2, yes, you are done.
But how can you put like 2 locations and it could still work in a third degree or third order equation?
No, because in the third order differential equation, first of all, it is not easy to solve it. But if you solve it, you get 3 parameters. Yes? So 1 condition will fix A. 1 condition will fix B. There will be another C somewhere, because that's a third order when you say. Then it means for fine-tuning the third one, I need the third piece of information. Yes? Okay, but by the way, let me ask your opinion about your understanding. Why do you think it is natural to have 2 free parameters if I have order 2, and it will be natural if I have 3 if I have order 3, and it will be 4 if I have order 4? Do you have any idea? Can you cook up a story for it? So I mean, why did you expect that a second order differential equation should have two free parameters in it? We studied that in Math 4, I think, yeah, I mean, that last session.
Is it because of the chain rule?
No. No, think. If I want to, by the way, we solved a problem like this exactly in Math 4 last time. Okay, so if I want to solve this second order differential equation, whatever it is, isn't it my goal to find x? Yes? So if I want to find x, this is the second derivative. If I want to find x, what should I do? Yes? F differentiation goes to f prime. Which one takes me back? Finding primitive function, or which I called fi. But when I go back, I will not get one unique answer. I get one answer plus a constant. Yes? So that's exactly the reason. Because if you want to go from y double prime to, from x double prime to x, you have to go to x prime, and then you have to go x double prime to x prime, and then to x. But when I go from here to here, I have to find a primitive function. But when I go from here to here, I have to bring in a constant of integration. Do you remember? Okay, and now I have one constant, I am here. But I have to go to the next level, so I have to do the primitive function once more, so it brings a new constant in. So that is the way that you need to imagine why, if I have order 2, I will have two constants. And if I have order 3, then of course I need to do this process once more, so it brings a new constant in. So that was not very surprising that if the order is n, I have n free parameters involved in my general solution. But there's also something that I might sometimes you say a singular solution. Singular solution is not part of your lesson, because sometimes it seems a little bit strange. Okay, by the way, can you solve this differential equation? Y prime squared plus y is equal to y squared is equal to 0. Okay, let us go back to Math 4 or math. So I am in math. So y is a function of x. So when I say y prime, my variable is not time anymore. It's just a normal math function. I am looking for a function. So first of all, let us review everything. Do you see that this is a differential equation? Why? Because it's an equation. What is the unknown thing there? A function y. And its derivative is also there. Here, first derivative. Okay, so that's a differential equation. What's the order? It's a first order, because the highest derivative is order 1. So the order of this differential equation is 1. Okay, but that's not probably very easy if you want to solve that. Okay, but now, can you solve this for me? It means I am looking for a function whose second power plus the second power of its first derivative becomes identically 0. I don't think it works, but let us check. So you say y equals to sine x. Let us check. So what is y prime? Is cosine x. Let us put it back here. So you solve a different one, yes? What is that? Because if you put y prime, it becomes cosine x to the power of 2. Yes, plus, I didn't know that. Okay, anyway. This becomes 2. And then this is 1, but it is not 0. So if I had given you this, then you solve the problem, yes? Okay, but let us take this one. And you told me this is this. Okay, but this is a general solution or not?
It's
Not, because you expect how many free parameters? 1, but you don't have. But you found a particular solution. Yes, because it works, but it does not contain any free parameters in it. But the question is that, can I find a general solution? I don't know if I can find a general solution. For example, you might say that, okay, Babak, let us multiply it by a. Okay, do you think it works? Let us check, because that is the motivation we got from the previous problem. Yeah, so let us multiply it by a this time. So y prime becomes a cosine x. And then y squared plus y prime squared becomes what? Becomes a squared. Because a squared sine squared plus a squared cosine squared, I factor a squared, becomes a squared. And that is no longer equal to 1 unless a is 1 or minus 1. Okay? So you see, this is no longer a solution. So I don't know the general solution, but I found a particular solution. Yes? Finding the general solution, I don't even know how can I solve the problem. Yes? But at least you can confirm that this is a solution to this differential equation. And that is the main, so that is one big part of your course. A differential equation is given, a function is also proposed to you, you are supposed to investigate if this is the correct answer or not. So this is no longer differential equation, this is a practice in differentiation. Yes, you differentiate the given function and put it back. If it works, you say this is a solution. If it doesn't work, you say it's not a solution. Okay? But now let me make that the starting problem. So can you tell me what is the general solution? What is the solution to this? At least something like this. So your example didn't work for my case. It worked for a different case. Yes, but it was good. Good that you say that. Okay. So now, do you have any solution for this differential equation? Can you imagine a function whose second power plus the second power of its derivative is 0? This is the simplest possible function ever.
Is it x to the power negative 1?
No, it doesn't really. If you want, I can check. Y is equal to x to the power of minus 1. What is the derivative? The derivative is minus x to the power minus 2. But then what is y prime squared plus y squared? It becomes minus x to the power of minus 2 to the power 2 plus x to the power of minus 1 to the power of 2. Yes? But this one is x to the power of minus 4. This one becomes x to the power of minus 2. And if you want, you can write it as x to the power of 4 plus 1 over x to the power of 2. Whatever it is, this is not equal to 0. Yes? Yes?
Is it y is equal to 0?
Yes. That's what I'm saying. That is the simplest possible. And that is the only solution. Can you tell me why? In your case, that was this problem. You told me y equals to sine x. We confirmed that this is true. But we cannot say this is the only one or not. Even I don't know if this is the only solution or not. But in that case, as Samir said, first of all, 0 works, yes? Because you don't like this is also a function, yes? Y equals to 0. What is that function? It takes everything to 0, yes? So that's the function, but what is its derivative then? 0. And if I put them back here, 0 to the power 2 plus 0 to the power 2 is indeed 0. So yes, that's the solution. But here I can claim this is the only solution. In your case, I don't know. Might be people can find other solutions. But in this case, this is the only solution. Why?
Because we found the free parameter from 0.
No, there is a reason why this is the only one. Yes?
Because since you square both of them,
Uh-huh.
they're both positive and one positive.
Both of them are non-negative. So this is whatever it is, I don't know, but this is non-negative. This is also something to power 2 that's also non-negative. And the sum of two non-negative numbers is either 0 or greater than 0. Yes? But I want to have it 0. Yes? So what is the only possibility? Both of them should be 0. So y should be 0, y prime should be 0. But y equals to 0 is automatically consistent with the second one, so that's the only solution. Okay? So what is the general solution to this equation now?
A 0.
Is? No, okay, a is 0, but there is no general solution because a is 0 is still 0. So you see that's what I'm saying, that here we cannot find any general solution. And y equals to 0 is a singular solution because it cannot be derived from a general solution. Okay? Okay, I'm not don't worry about these things. I'm just talking around this. What you need to know is I will not ask you to define these things, but I want you to know what is the differential equation, what is the order, And I want you to know what is the general solution, because sometimes in the book they ask you, is it a general solution? Motivate your answer. So how do you motivate that? If you want to see that something is the general solution, first, you have to show it works. Secondly, it should contain as many free parameters as the order of the differential equation. So when the time is finished, do you know?
30.
Okay, so yeah, let me give you one example of the type that you need to be for the exam. This is one of the type of the questions that you are supposed to know, and it's very, very simple, okay? So let me just give this example and we are done. If I write this, x squared minus 1, y double prime, and then minus 2x y prime plus 2y equals to 0. Okay. First of all, do you agree that this is a differential equation? Yes. What is your unknown function called here? Y. The unknown function is y. This is called dependent variable. Yes. And what is your independent variable here called? X, the other one. Independent. Okay. So it's a differential equation. Why? Because it is equality. In this equality, what is the unknown? The unknown is the function. And it includes some of the derivatives of the unknown function. That's a differential equation. So what is the order of this differential equation? 2. Why? Because even though you see the first derivative, you also see the second derivative. The highest order derivative is 2. So order of this differential equation is 2. Okay? This is a hard problem to solve. It's not that easy. But you will learn how to solve it if you go to technical university. Okay. If I want to solve this, how many free parameters you expect if you go to university? How many free parameters you expect to see in the general solution? 2. Okay, but we cannot solve it at this level. But I can give you a very simple question. I can give you y equals to 2x plus 3x squared, and then, if I remember, plus 3. This is one type of questions that you will get for the exam. A differential equation is given to you, no matter how complicated is that. A solution is also offered to you, and your duty is to confirm that this is a solution to the differential equation. So what do? You calculate what you need and put it in the left-hand side to see if it matches with the right-hand side. That's your duty. So this is just differentiation. It's math 4 actually. So what do I need here? I need y, I need y prime, I need y double prime. Y is already offered. So my duty is to find y prime, extremely simple. Do you agree? That's y prime. And I also need y double prime, which is 6 in this case. And then I start writing the left-hand side is equal to x squared minus 1. X, I don't know what x is, so I have to write x squared minus 1. But I know y double prime is 6. Minus 2x multiplied by y prime. Y prime is the whole combination. Yes? And then plus 2y. Y is the whole combination here. I have to simplify to see if this is the case, that the left-hand side matches with the right-hand side for every possible value of x. Be careful. So it should be identically 0. So let us multiply. So it becomes 6x squared minus 6. I multiply minus 2x in, so it becomes minus 4x minus 12x squared. I multiply 2 in, so it becomes 4x plus 6x squared plus 6. If I haven't done something wrong, everything should be cancelled out. Why? Because it insists that the right-hand side is 0 independent of x. Is that right or not? 6x squared here and 6x squared there, 12x squared minus 12x squared, they are gone. Minus 6 here and positive 6 there are gone. Minus 4x here, plus 4x there, it's 0. And that's equal to right-hand side. So you see, independent of what x is, the left side and right side match. So this means that I confirmed that this is a solution. But can I say this is the general solution? No. How many free parameters you see there?
1.
Free parameters. X is the variable. Free parameter is the constant that we add. There are no free parameters here. Yes? x is a variable, it's not free variable. Okay, so then this differential equation is of order 2. You expect 2 free constants, free parameters there, but you don't have anything of them, so that's not the general solution. It's a particular solution. Yes, is that clear? Okay, good. We stop here. Thank you.